Hello, and today's purpose of the day is I can simplify square roots, otherwise known as radical expressions. All right, the first part of notes on 10.2 simplifying square roots is we have to make sure that we have the radical in simplest form. So some conditions to make sure that the radical is in simplest form is if, number one, no radicals have perfect square factors other than 1. And think of perfect square factors as 4, as 9, as 16, because the square root of those numbers can be taken easily. For example, square root of 4 is 2, square root of 9 is 3, and square root of 16 is 4. And that can go on and on. The second bullet point says no radicals contain fractions, so we cannot have any fractions within our radical, and we'll take a look at what that means and go through examples. And then the third is no radicals appear in the denominator of a fraction. Okay, number one for the terms that we have to make sure radicals are in simplest form is if no radicals have perfect square factors other than 1. Okay, so as we look at A, simplifying part A, we have to simplify square root of 52. So again, here we want to look for like square root of 4, square root of 9, square root of 16, square root of 25, because we can easily take the square root of those numbers. And again, that list goes on and on and on and on. So let's look here. 52. What does 52 break down into? Well, I'm going to say 52 breaks down into the square root of 4 and the square root of 13, because 4 times 13 equals 52. And the reason I chose 4 and 13 is because 4 is a perfect square. So I actually can take the square root of 4, and that is 2, and I'm going to circle that because that now comes outside of my radical, because I, again, could take the square root of 4, and 13 stays under the radical because that can't be broken down into any perfect squares. Now, a way to check our answer is we can actually plug into our calculator our problem, and that was square root of 52, and then I can also type into my calculator 2 square roots of 13, and those will equal the exact same number if you type those in your calculator. So then we know that we'll be right, and that's how you can check your work. So my answer to simplifying square root of 52 is 2 square roots of 13. All right, let's look at the second problem on this notes portion. And part B says 2 times the square root of 24. And again, we know that they're being multiplied because these two terms are right next to each other. So square root of 2 times the square root of 24, if I type in my calculator 2 times 24, if I think logically about what is 2 times 24, I get 48. So now I have to break down square root of 48. So let's see, let's think of the largest perfect square that goes into 48. I could do 6 and 8, but then I have to continue to break down 6 and 8, and neither one of those is a perfect square. So I'm not going to use 6 or 8 because, again, not a perfect square. I want to think of perfect squares, and I think to myself 16 goes into 48 as well as 3, and then which one of those can I take the square root of? 16, and the square root of 16 is 4. So again, I'll circle that to remind myself that 4 comes outside of the radical, and then under the radical is still this number here that I can't take the square root of or break down easily. So my answer is 4 square roots of 3. And again, feel free to check this on your calculator by typing in square root of 2 times square root of 24. And if that comes out to be the same thing as 4 times the square root of 20, or 4 times the square root of 3, you are correct, and it does come out to be the same thing. All right, this last part C has a little bit more going on to this problem. I have not only, the square root of 45, but I also have variables. So I'm just going to break this down into two parts, and I'm going to first take the square root of 45. And now I think to myself, what's a perfect square that goes into 45? Well, I could choose 15 and 3, but that won't help me because 15 and 3 are they're not perfect squares. So I think of square root of 5 and square root of 9, and the square root of 9 is 3, so 3 comes outside the radical. I cannot do anything with the 5 or break that down anymore, so that stays under the radical. Now I'm going to look at my variables. So I'm first going to look at a to the fourth, and I need to take the square root of a to the fourth. And if we can recall from chapter 7, when we have exponents with the same base and we multiply them, we are really adding their exponents. So if we think about this, we really just want to take the square root of each variable, but really what we're doing with them, the exponents, is we're cutting them in half. Because if you think about a to the fourth, square root of a to the fourth, if you look right up here what I wrote down, a squared times a squared gives me a to the fourth. So I want to slice in half or cut in half a to the fourth, and the square root of a to the fourth is a squared. Again, because a squared times a squared gives me a to the fourth. But if we look at b to the fifth, that doesn't quite work the same way. It doesn't work the same way because 5 is odd. It's an odd integer, so I can't just slice that in half and say b to the 2.5 is the square root of b to the fifth. So what I have to do with an odd exponent is I have to break this down into one that's even and then one that's not. So it's easiest to just break it down into square root of a number directly less than 5, or the number that you're given that's odd, which would be b to the fourth, and b to the first, because now what can I take the square root easily? Which one of those two now is even, b to the fourth or b? B to the fourth is even, so I can take the square root of that, which is b squared. Again, because b squared times b squared gives me b to the fourth. Now, I can't do anything with this b that's left there, so that will actually be under the radical when I write my final answer. And last but not least, c to the sixth. I need to take the square root of c to the sixth. That is even, so I can just slice 6 in half, and out comes c cubed. So now when I write my final answer here, I have the number 3 that goes outside the radical, a squared, everything I circled again, b squared, and c cubed, and then what's underneath the radical is everything that's not circled. So the 5 right there, and b right there. And then that is my final answer. Now we are going to look at the second and third bullet points of no radicals contain fractions and no radicals appear in the denominator of a fraction. So we're going to do what's called rationalizing the denominator by making sure we can get rid of radicals that contain fractions and having no radicals in the denominator of a fraction. So let's look at A. I have 3n over 8, and that's all under the radical. So I can break this down into square root of 3n over square root of 8. That means the exact same thing. But this is now breaking a rule because, this radical contained a fraction. We just broke it up into square root of 3n over square root of 8, but now we have a radical in the denominator. So if I need to get rid of the radical in the denominator, so how I do that is I just multiply by whatever that radical is in the denominator, and that's how I'll get rid of it. So if I do something to the denominator, I also need to do that to the numerator. So now if I simplify this, I'll take square root of 3n times square root of 8, which gives me square root of 24n. I just multiply whatever underneath the denominator, underneath the radical with whatever else is underneath the radical. So here it was 3n and 8. And then the square root of 8 times the square root of 8 is the square root of 64, which is really just 8. So that's how I got rid of the radical in my denominator. But now this problem isn't complete because I have to break down 24n. And why do I have to break that down? Because I know there's a perfect square with 24. So I'm going to worry just about the 24 and not the n right now. So 24 breaks down into square root of 6 and square root of 4, and the square root of 4 is 2. And if you look, I can break down 6 into square root of 3 and to square root of 2, but are either one of those perfect squares? No, so it really doesn't get me anywhere by trying to break that down, but I could. So what comes out of the radical is 2. What stays underneath is square root 6. And now n is to the power of 1, so I can't break that down because that's odd, so I will leave that under the radical. So what I have here now is if I bring that right over here, I have 2 times the square root of 6n all over 8. But what can I continue to do with that 2 and 8? Break that down because those are both outside a radical, not underneath. So I take that, or I look at that as if it's a fraction, and I can take a 2 out of both, so this becomes 1 over 4. So my answer here to this problem is the square root of 6n all over 4. All right, let's look at part B, the second problem here. And this says square root of 6y over square root of 12. And that's again breaking a rule because I have a square root in the denominator. So how do I get rid of that? Again, I multiply by whatever is in that denominator. So I multiply by the square root of 12. And so that gives me the square root of 72y all over square root of 12 times square root of 12 is square root 144, which is just 12. But I'm not done with this problem because I need to break down 72 into the square root of 36 and 2. Out comes a 6. The 2 stays underneath. So does the y because y was to a power of 1. And so my answer here will be, change colors, the square root of, or 6 square roots of 2y all over 12. But again, I look at the 6 and 12 as if it's a fraction. Take out a 6, turns to a 1. 12 turns to a 2. So my answer is the square root of 2y all over 2. All right, here are a couple properties that I've pulled right from your textbook if you wanted to look at these some more. Again, this is just breaking down, the square root of a over b can be broken down into the square root of a over square root of b. And then the second property is the square root of ab can break down into square root of a times the square root of b. So feel free to look through these properties some more if you would like. All right, the last thing we are going to look at here is what's called a conjugate. So a conjugate means that we have a binomial in the denominator of the form of a times the square root of b plus c times the square root of d, or a times the square root of b minus c times the square root of d, where a, b, c, and d are rational numbers. So let's look at breaking down this conjugate. I have 2 over 4 minus the square root of 5. So how I get rid of that radical in the denominator, because again that's breaking a rule, is I want to multiply by the conjugate, which of 4 minus square root of 5, which is 4 plus square root of 5. Again, 4 plus the square root of 5 here would be called the conjugate. So if I do something to the denominator of a fraction, I also must do that to the numerator. So I'm going to multiply here by 4 plus square root of 5. Let me make sure that looks like a plus right there. So now, if I distribute in my numerator, take 2 and multiply that by 4 and by square root of 5. So 2 times 4 is 8. 2 times square root of 5 is 2 square roots of 5. Again, 2 here is not under a radical, so I can't directly multiply that with the 5 that's under the radical. So what I need to do is, when I multiply those together, the 2 just goes outside the radical, 5 stays underneath. And then if I look at 4 minus the square root of 5 times 4 plus the square root of 5, I am going to FOIL here, or I also could use the box method, and I'm just going to use FOIL. And 4 times 4 is 16. 4 times square root of 5 is plus 4 square roots of 5. Negative square roots of 5 times 4 is minus 4 square roots of 5. And negative square roots of 5 times positive square roots of 5 is minus square root of 25, which, what is the square root of 25? Just 5. So when I really look at this, the 4 square roots of 5 and the negative 4 square roots of 5 just cancel out, and I'm left with 16 minus 5, because again the square root of 25 is 5, and 16 minus 5 simplifies to be 11. So that's how we got rid of the radical in the denominator in this case, by what was multiplying by what's called the conjugate. So now I look at my answer here, and I have 8 plus 2 square roots of 5 all over 11. And I would try to look to simplify if there's anything that I could simplify, but there isn't anything. So this would be my final answer. There's no terms that I can, take out a factor with or break down. So that would be my final answer. Thanks for listening. Have a great day.